Alright, so this is a week one recap. It was like 2 days of class and one lab, so there's not much here. Alright, so I'm just going through differential equations homework. This one is classify as an ordinary or partial differential equation, give the order, and indicate the independent and dependent variables. If the equation is an ordinary differential equation, indicate whether the equation is linear or nonlinear. So this one here is a second order differential equation because we've got a y double prime term here. X is an independent variable in this case, and y is dependent because there's no partial derivatives here, and it's linear because it's in the form of something times y double prime and something times y prime, etc. Okay, this one's a partial differential equation. It's second order because it has second order terms. U in this case is the dependent variable, and x and y are independent. This one here, so when you write it out, x prime equals, you can multiply this out, you get kx squared, and you only have an x prime. It's first order because there's only one x prime. It's nonlinear because I'm not sure why that's not linear. Anyway, so we got dependent and independent. T in this case because it's all with respect to t. Oh, yeah, x prime. Right. Well, it's not in this form. That's why it's not linear. Okay, this one here. This is second order. It's not linear because the y is being multiplied by the y prime. Y is dependent, and x is independent. This one here, it's fourth order, ordinary differential equation. X in this case is independent and y is dependent. It's linear because it's just y to the it's y quadruple prime, I guess, and then it's equal to f of x. Because normally it needs to be in this form, but these are just 0, but there's a fourth one there, so that's why that works. Let's see, this is partial, it's second order. R and T are independent because these are done with respect to R and this with respect to T, and N is dependent in this case. Alright, write a differential equation that fits this description. So the rate of change of population at time t is proportional to the population at time t. So this is proportional to the population. So you can just put a k in there, proportionality constant. T is proportional to the rate of change in the temperature T of coffee at time t, proportional to the difference between the temperature M of the air at time t and the temperature of the coffee at time t. So the rate of change of the temperature of coffee is proportional to the difference between the temperature, sorry, that's the temperature, M of the air, that's M minus the temperature of the coffee. So this is going to be with this proportionality constant K. That's this first section. So this one here, we want to show that this is an implicit solution from this equals that on this interval. So what we can do is find y, knowing that dy dx is 1 over 2y. So what we can do is we can take the derivative of this and get this, and we say that it's equal to this, well, we're going to say that y in this case is this guy here. Y is going to be 3 minus x, the square root of 3 minus x, and that conforms to this one here. And this works for x equals negative infinity, because this needs to be positive root, and when it's not defined at 3. So dy dx is this thing. So let's take the derivative with respect to x of this thing, and then we're going to get this, and there's a lot of chain rules in here. So xy cubed, the x drops out, and then this is 3xy squared dy dx, right? Because we're going to do both of them implicitly. This one is the negative 3y cubed. Wait a minute. Oh, I took the derivative of sine x. So I did that one there. And then this one here, we're just going to drop the x out. And this one here, we're going to have a y prime because we did it with respect to y. And I'm going to factor out a y cubed. Plus, and I'm also going to factor out the y prime terms. And then I'm going to get this, and then dy dx times this stuff. And if I take this and divide it by that, I'll say dy dx equals this, which is the same thing we started with. So that works. Determine whether the given function is a solution to the partial differential equation. So we got that, and we also have x double prime plus x equals 0. So we said that x is this. Let's find x double prime, so we get that. So x double prime plus x equals 0. Well, 0 equals 0, so this one is a solution for this one. Okay, x equals cosine 2t, and dx dt plus tx equals sine 2t. So let's find x prime, and then we'll plug this into here. So that's x prime plus t, and we have x, so that's x, and that's not equal to this, so that's not a solution. We got y equals this, so y prime is this, y double prime is that, y double prime plus 4y equals 5e to the minus x, and let's see, so these guys, that cancels out with that, e to the minus x, e to the minus x times 4, so that'd be 5e to the minus x, it is equal to that, so that works. Okay, so keep going. So, what we're doing here, so we got dy dx equals this thing. Okay, so I took this one here, dy dx, took the derivative of this with respect to x. So we got y prime and minus 1 over y, that's the natural log of y times y prime, plus this with respect to x. And then, so we're going to do that again. Oh, sorry, we're going to factor out that dy dx equals this, so we can find what dy dx equals. And that's equal to this, which goes to that, which is the same thing we had, so that works. Alright, e to the xy plus y minus x to the equals x minus 1. So this is what dy dx is. Well, let's take this and just take the derivative with respect to x. So this one here, that's e to the xy, so that's going to be y e to the xy, and then x e to the xy dy dx plus dy dx, and then this one just goes to 1, and then we'll take this dy dx and factor it out, and we moved, what did we move? We moved that over to here, and then dy dx is this, and if we multiply the top and bottom by e to the negative xy, we're going to get this one here, which is what we wanted. Okay, so sine y plus xy minus x cubed equals 2. y double prime is this shit. So let's take the derivative with respect to x of this. We're going to get this. So we do that again. Yeah, we're going to take the second derivative of this so we can get y double primes. And now we have this. And then y prime is this. We're going to see, we have this in here, so we're going to go ahead and rearrange this for that. So everywhere we see that, we're going to replace with this. So we get that. And I wanted to get y double prime by itself, so then we have this over here, and y double prime equals that, and it's the same thing as this one. That's a little hairy, but not too bad. Okay, so this is one I did tonight. Yeah, so what we're gonna do is, this is theta. We can pretend that it's just like a y placeholder. So we got that, so let's take that with respect to x, and we get this. And there, so we have, now we have that equal to this stuff. And now we're going to take this, we're going to rearrange this to solve for c, because it wanted to find where c is an arbitrary constant of one parameter family solution. So we're going to try to find c here. So everywhere where we find c, we're going to plug into here. And notice that's going to cancel out our e to the x term, so that goes away and we get this. And then we're going to multiply that out to get here. And I'm going to multiply by the inverse over here just to get this. So we have that, and then I'm going to factor that theta out. And it's equal to what we had here. So that one's good. That's verified. And now it wants us to graph it. Not interested in doing that. So I just copied that graph down. Determine for which values of m the function is a solution to the given equation. Okay, so we've got theta. Let's go ahead and take the first and second derivatives to get these guys. And we just plug those into our equation here. And then it turns out that we get a quadratic, and we're just going to solve for m. So m is that and that. And in this one, we have the same things. So we're going to plug those into our equation, and we get our quadratic and solve for the roots, and that's m there. That was it for the DE homework. Circuits 2, it was pretty much just a recap of everything. I really knew all of this already, so I don't know that I need to go over it again, especially again in this video. Just a review of different circuits, circuit analysis, basic shit. I mean, how to do the matrices and whatnot. I always just make sure I take good notes, because if this is in this semester, it's good to have it all there, but I don't need to worry about it. Deformable, there's nothing covered other than the core syllabus this week. Now, I plan to read over and review lesson 1 in the book, because that's our first lecture, and I'm rusty on statics, I know that much. Okay, economics. I couldn't even see the board from the back. I forgot my glasses, so I got some notes from a friend, and he hooked me up. But anywhere I have these, I'm supposed to be putting slides in, but none of the teachers put their lecture slides up yet, because none of them have Brightspace. But anyway, so that's where that's going to go when I get there. But we basically went over simple interest, which is this. These values are explained here. That's where the interest is based on the principal, not the principal plus the interest gained. So just need to keep that in mind. So here's an example. We got 10 grand. We invest 10 grand. Our interest rate's 8%, and in 4 years is how we're gonna take the money out. This is how much money we're gonna get. Compound interest. So basically, our money is earning. It's not just based on the principal; it's the principal plus the money generated per interest cycle, which is n, right? Because number of interest periods, rather. So you can't really see the huge difference between these two, but this goes it's an exponential, so this one's going to skyrocket off. You can leave this one in the dust. Short term wise, you're probably it doesn't. I mean, you're better off with this one anyway, but you're not going to see much of a difference between the two. And some cash flow diagrams. Basically, whenever this is from your perspective. So if you take out a loan, or sorry, if you invest 10 grand, which means you pay 10 grand, and you invest it for, like I did in my example problem, that's what it's going to be. The payout's going to be. So, and from the bank's perspective, they just made 10 grand off you, basically. But when they got to pay out and they get this much. However, there's no bank in the world that'll just give you that good an interest rate. But that's just a demonstration. Okay, probability and statistics. Let's see. We've got well, a population is basically an entire group, and then a sample is a subset of that group. Univariate, it basically means like you're looking at one thing, like say males and females or something. Or bivariate, you could say I don't know, heterosexual males and gay males and heterosexual females and gay females or something like that. Anyway, that'd be bivariate, and multivariate is when you're looking at multiple criteria. So descriptive statistics is what we're looking at for the first bit. We have graphical ones, which is like a stem and leaf plot, histograms, box plots, and then the calculations involved are things like mean and standard deviation. Anyway, so all he went over was a stem and leaf plot, because this was like toward the end after he had told us about himself. So yeah, let's just look at it. So example, like we've got our pool of numbers. Well, these will be the stems. So we got 190, 170, etc. We're going to keep going through this way. This is like height in centimeters. So you could do, so this is 160, 160 is in here, and 169 is in here. So this would be 09. So you're just using like the last digit. Or if you wanted to break it up even more, you could do 16 and then lows, which would be from like 0 to 5 or whatever, or 0 to 4. I should have wrote it down. I don't remember. Because there's no 5s in here for me to tell. But yeah, you can just split up like the ranges if you want a little more examples. But every single digit you see here is going to be one of these numbers covered. So we have 1, 2, 3, 4, well, it doesn't matter. These are all covered in here. So that's it for that. Design 2, this is just kind of an overview. Logbooks. There's a logbook that we have our hands on now. Maybe I should just go into Arduino. Let's see. I'll just open up my sensor lab. Okay, so there's a couple libraries we used. So we're including this servo library. This servo library is like just a standard one that you can include, but it gives you access to an object called a servo. So I created all these things here. We had to design a circuit with 2 push buttons and rotate a motor and turn on an LED. It was to move an arm up and down. But anyway, so in my setup, I've got all these made, and in the setup I'm just gonna go ahead and say serial.begin. This basically sets the baud rate of the Arduino, so it's just so that like we're not sampling too quickly, so that when you do a button press you get bounces and then it triggers things wrong. But anyway, so these are me setting up the pins. So I've got one called LED pin, that's going to be an output. It's pin 13, pin 10 was one for the button, and pin 11. So basically those pins are going to be inputs to see if the button's being pressed or not. And yeah, so anyway, and we got myservo.attach. So this means this is just in the object where we specify which pin the servo's on, and then write in microseconds This one here, based on the motor we were using at 1500, it basically ranges from 1000 to 2000, and 1500 would be like center, so it's not moving when you use 1500. So basically, button 1 state, which I made with, as a boolean. This is just, we want to check and see if it's being pressed or not, and we're checking button 2 also, and then we have an if statement for button 1. So what it's going to do is make the LED high while it's being pressed, and then it's going to rotate the motor. I guess this was lifting the arm upwards, so I guess it's counterclockwise. And then we're going to wait 1 second or 1000 milliseconds. And then if it's not being pressed, then we're just basically keeping the LED off and making sure the servo is not moving. And then we do the same thing for button 2. And yeah, so we're going to, if button 2 is being pressed, which means it's going to be a boolean, it's going to be 1, so it'll enter that statement. Same thing, except in this case we're just going to rotate it the other way. And that's pretty much it. So that's that was our little tiny week 1. So the next video should be a recap of week 2. I expect to get a lot more in one video, but I think this is really good for me to do recaps like this. Except, you know, recaps of courses I had just done previously. But yeah, I know all this stuff anyway, for circuits at least. I'm not too worried. Anyway, that's it for this week.